Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. This particular lecture is actually like slightly deviate from the last two lectures. So till now what we have seen kinematics and differential kinematics, but here we are going to talk about what you call statics. What that means, for example, I have a 2R serial manipulator. Okay. So this 2R serial manipulator is having a end effector. This end effector is carrying a load. Okay. So I assume that it's a mass. So it is actually like y and x, and this is having a gravity. So now it is actually like pulling down. So now what idea is actually like coming here. So if I want to actually like keep this location as theta 1 and theta 2 frozen, what I need to actually like provide a torque. Okay. So what torque I have to provide here as tau 1 and tau 2, so that this configuration would be, you can say, standby, in the sense it would be static equilibrium. So this is the actually like case we are actually like going to attempt. In the sense what we are going to see, we are going to see the statics as the main ingredient in this particular lecture. So let us actually like move to the original content. So we are going to talk about statics. So we are going to give a relation. So the relationship, okay, so between end effector effects, so I call the end effector or task space efforts. So efforts to what you call the joint space, you can say, inputs. So that is what we are trying to see. If you recall the previous slide also, you can see like, so if I give the payload here, so what would be my inputs tau 1 and tau 2, that is what we are trying to see. So this relationship I am trying to find out, in the sense you have end effector forces and moments. So that I am actually like trying to relate as tau and small f. Okay. So this relationship I am trying to bring it here. So that is the whole idea of the statics. So then you know already, so the Jacobian may be singular certain instant. So why that is happening and what instant it is happening. So then we will bring that called singularities. So what kind of singularities are exist in the serial manipulator, these all we are going to see in this particular lecture. But I am going to give a small disclaimer here. So we are not going to see the singularity in detail, because this course is mechanics and control. We are not going to see the singularity in detail. We are just giving a introduction and a small you can say idea about singularity and types of singularity. Let us actually like move to the static case. So you all know like static equilibrium means the sum of, you can say, all forces would be 0. Similarly, sum of all moments would be 0. So now if these two conditions are exist, so I take a random link. Okay. So I am taking a random link. So this is actually like a random link, which is actually like I call link I. So in the sense this is ith frame and this is I plus 1 frame. Okay. So now if I have a force, okay, force at I plus 1 to I plus 1, can I actually like get the force of I? Okay. So in the sense we are trying to come backward. Why it is actually like backward? Because we are actually like talking about the serial manipulator. The end would be actually like clearly known. How we said that the velocity propagation from the base, because the base velocity and acceleration would be known, we would be doing a forward propagation. The same way the end side is actually like your task end, that would be known. So from there we are actually trying to come back. So that's why it is a backward propagation, in the sense if you have Fn, okay, so can I find the F00 or not? So this relation we are trying to derive, that too like we assume that that configuration is frozen, in the sense there is no work has been done. So that is what the whole idea, in the sense we are going to use the static equilibrium. If you take a link I, in the last you can say picture I was showing, so you take the link I, So now you can actually like see that there is one force acting. So this force is actually like I plus 1 to I plus 1 frame. If I want to convert here, so what I need to do, so I can actually like multiply that, okay, with respect to this. So this will give what? So f I to I plus 1, right? But what one additionally you should know, this is actually like statically equilibrium, in the sense static equilibrium, in the sense the cumulative forces would be 0. So if that is the case, here what are the forces would be acting? So one force would be I to I, okay. So then there would be another force would be I plus 1 to plus 1, but we are actually like writing it right now, we are actually like seeing everything in the ith frame. So then what I am actually like writing this ith, because we are actually like seeing in ith frame. So this supposed to be 0. So whether we are actually like putting plus sign or minus sign, that is actually like based on your representation, but what we are saying, the sum of f with respect to I frame, with respect to I frame, so that we are actually like equating to 0. So that is what the whole idea. So if that is the case, so what you will get? You will get this relation, okay. So that's what I said, the sign is actually like up to us. We assume that f I to I supposed to be equal to f I plus to I. So then only this equation would be valid. So we are taking this way, so then we are using this equation. Similarly the moment, so the moment also like you can see like this link, okay, this link would be having another, you can say link having a ith joint and I plus 1 joint. So this would be having an angular moment, right, and this would be having a force vector I plus 1 to I plus 1. So these two would be generalize, you can say generate the torque at ith frame. So that torque, how I can actually like write it? I can actually like write it as in this form. So what that form? So you can see like this is what we wanted, but that is actually like represented from the previous, you can say, or you can say a proceeding joint angular moment, okay, and the proceeding, or you can say previous, you can say before joint forces also acting. So now you should be clear, omega cross r would be linear velocity and r cross f is the moment. So the direction should be very clear. So now you can see this is equal to r cross f, okay. So this is what the static equilibrium condition. So whatever we have written, this we have written in this form. So now we can write this as a propagation model, in the sense backward propagation model. So for that what we are rewriting, we rewrite this equation in this form. So where we are actually like equating this equal to this. Similarly we are equating this all equal to this form, okay. So in that sense these are the two equations, but what I said, this I plus 1 to I plus 1 the force, and similarly the I plus 1 you can say angular moment with respect to I plus 1 frame is available. So in that sense I can actually like multiply that with this matrix, this will give, so I plus 1th you can say angular moment with respect to ith frame would be obtained. So similarly here if I actually like get, this is actually like force vector of I plus 1 with respect to ith frame would be obtained. So this is what we have used here. So now you can see this is the backward propagation model, because we start from n to 0. So now based on this we can actually like derive the force vectors and angular moment. Right now we are not going to use that, but we have some relations, right. So what relation we have? So we have actually like these relations what we have written already. So what we have is actually like this virtual work. So work is a dot product that we know as a vector force, a torque and a vector displacement. But what we can see that right now, I am just giving an idea, okay. So now this is a simple pendulum, I am putting a force here. So how much actually like this force displaced, okay. So that would be corresponding to the displacement happened on the, you can say, the input side. So in the sense the total work done and virtually is 0. So but what we can actually like write it in the other way around, whatever is work done at the end effector level, that's supposed to be equal to the you can say the configuration or joint space level. If that is the case, the joint space torque vector written as tau and the end effector force and you can say moment written as capital F, and you know delta mu is actually like the change in displacement in mu vector, and the delta q is change in displacement in the joint space or you can say joint angles. So now this we know, but the dot product I can write as a transpose, right? So this I can write, and we assume that this delta q and delta mu happened on the delta t time, and further this delta t is very small, very close to 0, or delta t tends to 0. So what we can write? We can write delta mu as j of q into delta q. So this relation we have. So now if you substitute, what it will come? So the tau transpose is f transpose into j of q, where you take transpose throughout. So what you will get? So tau is j transpose of q into f, right? So this is what we are actually going to call as a relation. Now if you know the end effector forces and your Jacobian matrix from 0 to n is known, so then what you can see? You can find the static, you can say efforts at the joint, whatever required, that you can calculate. So that is what we have actually like a detailedly written, you can see, and for a smaller time duration you can write this. So if this is valid, this can be done, right? So once this is actually like done, so this is what the final relation come. You take transpose throughout, so this whole transpose would become tau, and you take whole transpose, then this would be interchange with the transpose. So that is what we get. So this relation you know, because j of q can be obtained with the velocity propagation. So now j of t transpose only, right, required, and you know end effector forces, you can calculate what would be the input required to maintain that static equilibrium. The same relation some people would have written based on the conservation of power. So what that means? You can say the power happened, we assume that there is no losses, in the sense whatever power happened at the output end, in the sense task end, that would be equal on the configuration end. So that is what the case. So that is what we have actually like written. So in that sense we can actually like write that as a vector product, or sorry, dot product. So that dot product actually like we can write it as, so tau dot you can write as q dot, which is written as f dot dot is mu dot, sorry, this is f, okay. So f dot mu dot, okay. So now this relation we know, and again we can use the dot product as vector basis. So this is what the relation, and then you know mu dot already, j of q into q dot, this relation we know already from the forward differential kinematics, and you substitute, now finally you will get the same what you call relation. So here, okay. So this is what we obtain, and finally we will get this. So this is the other way of finding, but we always use principle of virtual work. So this is conservation of power. So both are actually like giving the same what you call relation, but this relation we can use it. So now, so one thing we supposed to know, what the other thing. So based on the j of q, if the determinant is 0, what we can actually say, it is singular. So when this will happen? So whether the robot is actually like serial, the two redundant or not, it is actually like possible some cases where the Jacobian matrix, the determinant would be 0. So what cases it can happen? If the prismatic joints are there, that become parallel, or if it is actually like revolute joints are actually like identical, or it is actually like collinear. For example, you take this as a serial manipulator which has 2R. So now if you are actually like rotate this, make it parallel. So what happened? You are actually like having theta 1 and theta 2, but now this theta 2 is actually like 0. So now when I rotate theta 1, the theta 2 is actually like invalid, in the sense the theta 2 is actually lost its degree, because I want to actually like rotate this. So when this can happen? This can happen is actually like at extreme, in the sense, so workspace extreme case, or it can actually like come some other collinearity. So that is what we are actually like doing it. So in the sense what happened, the end effector would be inferior in the dimension. In the sense if you want to write, this would be function of only theta 1, right? In the sense what you are actually like, you are losing the theta 2. In the other way around, you are actually like losing the degree of freedom. So one or more, you are actually like losing it. So that can happen due to some situation. So that is what we are actually like writing it. So now you can actually like see that the end effector loses one or more degrees of freedom, since the kinematic equation become linearly dependent. So now you see that this is actually like a 2R serial manipulator, even I am making it a 3R. Okay. So now you can see these two are collinear, right? So this also can happen. Okay. The other way around, so you can actually like see this is, so this is another configuration. Okay. So another configuration where you can see that these two joints are actually collinear. This is also like reduce the dimension, right? So that is what. So but what indirectly it is giving, you see you have a relation, right? So mu dot is actually like j of q into, so q dot. So right now you have some end effector velocity. Okay. So you are actually like trying to find this as a q dot. So if the singular cases, what happened, the q dot would be infinite. Why? Because the j q inverse, or you can say j inverse of q, become a singular in the sense, so you can actually like see that the q dot become what you can say, the j q inverse would be infinite, so the product would be infinite. So in the sense, for example, you keep so you keep your hand, okay, so you can actually like extend. So now you can see that your elbow is actually like lost, right? So if you are actually like doing it, your elbow cannot have any, you can say, control that. So now if I want to actually like fold at this extreme case, I cannot create any force, right? Because it's required actually like infinite efforts. So that is what the whole idea, so that we can actually like discuss little bit in detail in upcoming lectures. So right now we will actually like see what kind of singularity can come. So there are two kind of singularity in serial manipulator. So one is actually like workspace boundary singularity. So for example, I am taking this is actually like a serial 3R serial parallel, or you can say planar manipulator. Okay. So this is the end effector. So this can actually like happen actually like at extreme, where this is the workspace. The workspace extreme, it can happen. Okay, this point and this point, it can be singular because it can be completely folded. Okay. The other way around, it can be happen, these two can be folded, still that would be within the workspace. So that is what you call interior singularity, the other one is boundary singularity. Workspace boundary singularity is actually like extreme. If you are taking a 2R serial manipulator, it has happened only the workspace boundary singularity, but if I add a third rotary joint, that would have interior singularity. Okay. So when this can happen, two or more axes line up, in the sense collinear. This is actually the extreme case, it cannot go beyond, it cannot go beyond like that. So these two are the two types of singularity. How we can calculate the singularity? So you have already the clue. So if you have a Jacobian matrix, you can take the determinant and equate to 0, you will get the singularity condition. If it is actually like a rectangular matrix, then you can use the J transpose determinant or J transpose J, so based on the size. Okay. So that is what we are actually trying to see. So we can actually like find this for a square matrix. If it is actually like a rectangular matrix, you can take J transpose J determinant or J transpose determinant based on the condition. Okay. Indirectly, which matrix size is giving a smaller one, that is what we are going to take it. Okay. So that is what the whole idea. So I am just showing a small example for here. A 2R serial manipulator, you know already the Jacobian matrix. So now you take a determinant. So what it will come, the determinant would be something. So finally you will end with this as the residue. So now you equate to 0. So L1 L2 is actually like link length, that cannot be 0. Then you can see sin theta 2 would be, this is the reduced form. Okay. So this would be 0, then theta 2 is actually like either 0 or pi or 2 pi. In the other sense, I can say n pi. Okay. So any n start from 0 to, you can say any number, 0, 1, 2, 3. Okay. So this is what the condition. So that is very clear. So when this happened, so very two simple case we can take. So for example, this is a 2R serial manipulator. Okay. So I am trying to show that when this can actually like a singular. So you rotate this and make it. So what happened, this is actually like a 0 degree, theta 2 is 0 degree. So what it says, it is actually like extreme, this is the workspace, right, the boundary. So now the same thing you actually like rotate the other side. So it is actually like come here. So in the sense it is coming here, what that, so theta 2 is actually like pi degree. So that is also like in this case it's a boundary. So these two boundary singularity is actually like realized from this case. So when theta 2 is 0 or pi, 2 pi is again 0 equivalent and 3 pi is again equivalent to pi, right. So now these are the two situation of singularity condition for a planar 2R serial manipulator. So we will see more detail in one or two example we will see in upcoming lecture. So with that we are closing this particular lecture, and the next lecture we will see few example. So how we can find the singularity and how we can find the static conditions. So with that I am saying thank you, see you then, bye, take care.